How can the FixedIT data agent, ACAP, reduce cost and problems with your network cameras and other access devices? It's no easy feat to manage hundreds or thousands of cameras. Ask your IT team if you don't believe us. Countless hours are spent debugging issues while accessing different systems, but it does not have to be like that. If we said that you could get all information on one single pane of glass, not only that, but you can get it in Grafana, a tool that your IT staff already use and love? What you can get with our FixedIT data agent, an edge application that runs in your cameras to monitor the system and the network. It then pushes data to an InfluxDB Grafana stack that you can self-host. It even buffers data locally on the device during outages. The dashboard is open source, and the Edge application is extendable using scripts and config files. This means that you can add logging of any extra information you like, and get everything on the same pane of glass. One system, one interface, thousands of devices. How can this benefit you? Integrators and solution providers. Comply with certifications and SLAs. Provide better experience for your customers. Save money on operations and sell extra services. Enterprise organizations. Save money on operations. Reduce system downtime. Ensure security and compliance. Developers and technology integration partners. Get detailed insights into the system and simplify benchmarking. Monitor your application test environments. Automate repetitive tasks. With our dashboards, you can use the type tag to mark different use cases, e.g., different versions of an application that you are benchmarking against each other, or different analytics use cases deployed to the site. You can use the geotags to mark region and site, and filter all the data based on these settings to compare uptime between offices. You can see exactly what Axis OS ran in which camera at which point in time, and when the type tag was changed from one use case to another. You can see new devices added and existing devices lost. You can go from the high-level overview to the device details by just pressing the host name. What more would you like to do?
And computer vision might be one of those cases where it is even more important to run your algorithms on the edge to avoid streaming massive amounts of data that in many cases are not getting used because you just look at them once with your algorithms and then you throw it away again. So then it's better to move the algorithms to the edge. And this could be everything from parking space monitoring, detecting if a parking spot is occupied or not. It can be QR code and barcode decoding for logistics, for access control, for tracking inventory in manufacturing processes and so forth. It can be digitalization of analog equipment without doing physical harm to the equipment. It might be automation, custom sensors in manufacturing. To the top right here, we see some empty bucket classification that we have done as a POC, where we look at if it's possible to detect if a bucket is full with white powder or if it is empty, using segmentation running directly on the camera. And we have optical character recognition. We have sports analytics, both aggregating statistics about the players. For example, how much active time does this player have? How long have this? How long distance have this player been running? But also to do more real-time insights, such as controlling the camera to focus on the most interesting aspects. It might be things in intelligent manufacturing and visual quality assurance, such as measuring the sizes of items or looking for scratches or other kind of defects in manufactured objects. License plate recognition, of course, for access control especially, or to ensure the safety and security around critical infrastructure and so forth. And it could be smoke detection, fire detection, detecting hot places with thermal cameras, or it could be flood detection or other kind of water analysis. So the use cases for computer vision are essentially unlimited, and it's just your imagination that limits you on what product you can build. At least if you know how to program together with Axis devices, because then all these deployments or products will be made possible. So why do we like the Axis cameras so much at FixedIT? We think that network cameras are very easy to install and very easy to connect to your network or to your infrastructure. And the reason they are so easy to install is that they all come with good enclosures and good mounting hardware. And there's a massive inventory of different kinds of mounting hardware for mounting it in different locations on different items and so forth. So they are very easy to install, and there are system integrators all across the world that can do the physical installation for you if you don't want to do it yourself. And one aspect that many people forget is the importance of having a large amount of different camera models available that you can interchange between or when using your product, and especially the importance of different kind of certifications. So we have, for example, seen many customers who start with one application in one particular environment where they might not need any specific certifications. So they just take one of the cheapest cameras. But then the next customer comes after they have spent all this time developing the project. The new customer come and say that we are going to put our cameras in this particular environment where we require this certification. And for our customers, this is typically not an issue, since they have built their application for the Axis network cameras. And Axis have a large amount of different models that are classified for these different environments. So it might, for example, be that you need to install it at a refinery, and then you need an explosion protected camera due to the classification restrictions there. It's not allowed to put up any other electronic equipment that isn't protected from igniting explosive gases and so forth. But there's also a lot of other devices like strobes and network speakers that we will see a little bit of today. And they are all running the same ACAP platform, which makes it very easy to create applications that are portable between the different devices. So when we talk about edge compute, edge AI, and so forth, the idea is often to move the algorithms to the site and run the software there instead of running it in the cloud. A few different devices that are commonly used for this are things like Raspberry Pi, NVIDIA Jetson Nano, Esperif ESP32, and similar microcontrollers, and the Intel NUC. And as you can see, these ones aren't really designed for these kind of harsh environments that you often get in the real deployments, both software-wise and hardware-wise. And hardware-wise, we might, for example, look at outdoor installations, and then you need IP ratings that make sure that they can stand years of harsh weather, and it might even be large temperature variations, everything from freezing environments to 40, 50 degrees Celsius hot environments in the desert. But it might also be that you need IK classification, for example, to make sure that they are robust against people trying to destroy them. In retail, for example, you might have restrictions from a fire safety perspective that you're not allowed to just put a Raspberry Pi on top of the hidden ceiling, for example, because it would be a fire issue to do that. So you need specific classifications or certifications there too. If you ever try to install a camera in a farm, you have probably seen that when they clean the barns, they go with high pressure washer and they spray it all over the cameras to get rid of all the dust and other dirt that gets on top of the lens. And with Axis cameras, that's not an issue if you have selected the right camera. And then, of course, for industrial locations, you have everything from food graded locations where you need to have the right restrictions to make sure that there can't be any bacteria growing on the enclosure of your device. But it might also be refineries, for example, or a lot of other industries too, where you have some kind of explosive gases or explosive dust that could be put on fire by electronic equipment. So you have an access network camera and you want to start using it. Connecting to it is super simple. All you need to have is some kind of Ethernet with power over Ethernet, which means that the camera will be powered with a single cable to get both connectivity and power. And once you're connected to the same network, you can access the built-in web server in the camera and communicate with it that way. And the very nice thing here is the power over Ethernet, which makes it so easy to install since you just need a single cable. So if you don't have a PoE router, then you can have a PoE injector that you put just on the cable to inject the power instead. And software-wise, we think it's super nice that you don't need any custom hardware interfaces in most cases, since you have a web server built into each individual camera. So you just connect it to the network and then you can access it. So let's do a super quick demonstration here if someone would not have seen these interfaces already. So this is typically what you see when you work with one of the access cameras. This is a Q1728. It's placed right here next to me. And we can see that this is the IP address of this actual camera. So all this is hosted inside the camera itself. And here we have the live view, we have status information, we have configuration of different kinds, and we have applications that we will soon have a look at. And if we head over to this camera, which is sitting over here, I don't think you can see that. This is a PTZ camera, meaning that we can move it around. There's electric motors in it moving the lens around so that we can pan and tilt and zoom around and look at whatever is interesting for us right now at this moment. So that was a very quick overview on the access cameras and what you can do with them through the user interface. But what we're really here to talk about today is how to do these things programmatically. So the reason you want to do this programmatically is, of course, because you want to automate the control. You want to create a scalable product or an automated solution to solve your problem. And the easiest way to do this with access cameras is to use the network APIs. And this comes with pros and cons, which we will discuss. But let's start to just show how we can do this. So I'm going to change to this Python editor here. And what we're going to use in this demonstration is the network APIs called VAPIX, which is Access own network APIs. We will see later that there is also another parallel API track called ONVIF, which is an open standard. But in this demo, we will make use of Access own VAPIX APIs. And VAPIX APIs are web APIs that essentially allow you to do anything you can do from the user interface and a bit more through programmatic requests to the camera instead over the network. So this is a script that I will run on my computer, and it will communicate with the cameras that are next to me here. So what I have done here is that I have created the script in Python because I'm a big fan of Python. I think that's a very nice programming language. Since it's all web-based APIs, you could make use of any programming language you want to. I have created a class here, which is using the URL to the camera and authentication using a username and a password. And down here, when we instantiate the class, we will give it the IP address, username, and password for the device. I have then implemented two different positions, move to position, two different functions, move to position and get current position. So these are part of the PTC API. And the first one allows us to specify a position that we should go to in degrees, and the second one allows us to get the current position. So if we execute these cells, we can see here that currently our camera is located at 82 degrees pan, minus 17 degrees tilt, and a zoom value of 68. So these two are in degrees, while this is a number between 0 and 10,000. So it's always normalized to that range, regardless of how much zoom your actual device have. So let's now try to make a command to move the device and see if we can see that. So if we, sorry, where do we have the browser? Here we have the browser again. So now we can see that the camera is moving between these two positions. So what our code does is to first go to one position, wait 5 seconds, then go to another position, wait 5 seconds, and then go back again. So that's really how easy it is to get started with programming to interact with your devices. Let's have a quick look at the other option, ONVIF, which is this open initiative API standard for network cameras. So the big benefit with ONVIF is that a lot of camera vendors do support it, most camera vendors in fact, while VAPIX is only specific to access devices. That means that VAPIX, if you use that, you tie yourself to the access devices, or you will need a different implementation for different camera vendors. But if you use ONVIF, you would be compatible with all the different or most of the camera vendors. The drawbacks, in my experience, is that for the access devices, for example, you don't have as large coverage on the functionality in the ONVIF API standard as you have in the VAPIX settings, especially when it comes to different kind of configurations of the camera. There's more things you can do with VAPIX than what you can do with ONVIF. And another drawback is that, in my experience, the quality of the implementations of ONVIF are not as good as the quality of implementation of VAPIX. And this is probably because it's not a standard owned by the company implementing it. It's a standard that is negotiated between multiple parties, and then each of them go out and try to implement according to that standard, which I think is quite a lot harder than if you can design the standard based on your own environment and hardware and so forth. But in this case, we can see an example where we make use of an ONVIF library that exists for Python. Other languages probably have similar libraries, but you could, of course, do as we did with VAPIX and go directly to the network level stack and run the network APIs directly. In this case, we are using the ONVIF library to connect to a camera and then get the user accounts in that camera. And it's worth noting here that the username and password that we make use of for the VAPIX communication is the same as the ones we have in the user interface for the camera, while the ONVIF users is a separate account or pool of account. So we need to manually create an ONVIF user before we can use the camera with ONVIF. So let's talk a little bit about the challenges with interfacing with the devices in this way. As my old manager used to say, paint it blue and ship it. We have a script that is working. It's creating a guard tour between two different positions using a PTC camera. So what's preventing us from just shipping it, start selling it as a product? Well, the question is, where should the code run? Now I run the script on my computer, but if we build a product around this, my computer won't be there. Will the customer have a computer that can run the script? Do they have the right environment set up on their computer? Should they install a computer specifically for this? And in that case, should we use one of those that we looked at earlier, the Raspberry Pi or the NVIDIA Jetson Nano, for example? And then we come back to all these things about the classifications, the certifications. Do they have the right certifications? But it's even more complicated than that, and especially if we try to create a cloud-based system, because we might think that AWS have easily accessible, easy to computers that we can make use of. But then we have the problem with internet and firewalls, that reaching a camera or a network device in general over the internet isn't always easy due to the use of firewalls. So if our computer, either my client or a server running in Amazon Web Services or anything anywhere else, is making a request and trying to access a camera that is not in the same network, then we will go over the internet and we will have the first issue with a firewall at this customer site, which does not allow incoming traffic. So the old traditional solution to this is to do port forwarding in the router. So essentially, we would tell all your customers that we need to access all your cameras on this port, and you need to go to your router and add a configuration that opens up for incoming traffic from the internet. And this is not a good idea. Firstly, it's very complicated. It's a lot of work for the customer to do this. If they have a lot of cameras, they need to do this for each camera individually. Firstly, they need to know what port number and IP they should forward to. So the port number is hopefully easy. You should know what port numbers you're needing to interact with the devices. But then they need to know the IP address of the internal IP address of their camera that they are forwarding the traffic to. And the problem with this is that this is often set using dynamic DNS. So then you get into the issue, what happens if you set port forwarding to one IP address and then your camera changes to another IP address? Then you would first not be able to reach the camera anymore, but it might even open up a vulnerability because now something else is sitting on that IP address and have an open gaping hole from the internet into it, which it doesn't expect. So that's one of the issues. And then you need to know the external IP address of this customer's network so that you can make your request to that IP address. But the problem is that internet service providers typically use dynamic IP addresses, which means that every now and then they are changing. So it might work for a month or two, and then suddenly there's a new IP address, and there's not really any way for you to know that IP address without having someone go to that particular network and make an outgoing request to see what IP address they have. Or you can pay extra to get static IP address, but this option is not practical, it's not safe, and it's generally frowned upon by customers if you ask them to do this. And one of the issues is, of course, that you make it a little bit too easy to access the camera, because anyone on the internet can now go in through this hole in your firewall and access your internal system. So then you only have one line of defense, which is the security functionalities built into the network device itself. So another common option is to use VPN-based solutions. So VPN is essentially a way where you can run one software on the local network, and you run another software on your client that is on another network. And essentially it creates a tunnel through the internet to that network. So it looks like your computer is on that very same network. And that would allow you to make requests directly to the cameras, just as if they were on your own network, as I did now. But the problem with this is that you need to run VPN servers. It's a lot of complicated infrastructure that should be set up. And running a dedicated server with a VPN isn't really helping in a lot of cases, because that server is what we want to get rid of. And especially if we look at modern distributed systems, typically network cameras were used in surveillance situations where we had a lot of cameras on each site and a few sites. So you might have had 100 or so different chains, and each of the chains had maybe 1,000 cameras. But now it's often the opposite, that you can have thousands of sites around the world, and each site is often very small, maybe just 1 or 2 or 5 cameras or something like that. And then it doesn't make sense to put up all this extra infrastructure on the site. Then you want the camera to be able to communicate directly with your cloud service or whatever infrastructure you have. And typically, outgoing traffic is almost always allowed from these kind of networks. So that's typically what you want to make use of. You want the camera to do requests out instead of doing requests into the camera. And that's what you can achieve with using custom ACAP applications that you install directly in the camera, where you can add your functionality and they will push data outwards instead, or make outgoing requests. Then you want the camera to be able to communicate directly with your cloud service or whatever infrastructure you have. And typically, outgoing traffic is almost always allowed from these kind of networks. So that's typically what you want to make use of. You want the camera to do requests out instead of doing requests into the camera. And that's what you can achieve with using custom ACAP applications that you install directly in the camera, where you can add your functionality and they will push data outwards instead, or make outgoing requests. So one example of this is our FixedIT data agent, which is an application that you can use for monitoring your devices. So essentially what this application does is that it runs in your camera and it collects a lot of metrics about your system. And then it is pushing that over a protocol to a database that you can host somewhere, either in the cloud or in your company network. And here you can create Grafana dashboards and alarms and so forth to keep a track of your cameras, both proactively and reactively, to see how they are doing and that everything is fine. So let's take a quick example of how this can look in our case. So if I go back to this camera here and I go to the apps page, then we can see that we have the Telegraph agent running here, which is our data agent. And if we go into this one, we can see it's running and it's currently pushing data to the to our InfluxDB server. And that data we can now access in our cloud-hosted server, where we can have a look on the overview of devices, and we can see what devices do we have connected to this system. We can see the historical trends, such as CPU and memory. We can see uptime and so forth. And we can also see what kind of device it is. We can see what is the external IP address. So this was one of the issues that we had with networks, that we don't know what IP address they currently have, since the ISPs use dynamic IPs. But using this application on the network that is continuously pinging us and telling us the current network IP address, that allows us to know where it is located. And we can see the local IP address on the local network, and we can see when we last had a ping from the device. So that is one use case for creating an edge application. Another way of solving this issue, instead of doing port forwarding, is something we have done for a few customers with our FixedIT SSH connector. And this connector is essentially running an SSH client on the device that can set up tunnels based on your requirements to your own SSH servers. So this is a little bit similar to using a VPN server, but instead of requiring that complex infrastructure, all you need to have is an SSH server, and it will automatically connect to that system and forward its own ports using a tunnel. And the benefit with this or one of the many benefits with this compared to doing port forwarding in your router, is that we don't have any area exposed to the internet, since it's just exposing its port to this specific server. And another one is, of course, that you don't need to do any configuration on the site, because from the site it just looks like this device is doing outgoing requests to the internet like any other network devices typically do. And it has the added benefit of tunneling all traffic over TCP. And if you have ever tried streaming RTSP, for example, over a 4G modem, you might have had issues with either it not working at all, or that it takes a long time for it to connect, which is probably that it first tries with regular RTSP, which is UDP based, and often that is not allowed by the 4G internet providers. So then your client might fall back to RTSP over TCP or RTSP over HTTP, which might go through the firewall. But with this kind of forwarding, all the traffic is always tunneled through the same protocol. So from the firewall, it always looks like just outgoing SSH traffic. So edge compute, edge AI, edge applications, simply moving your workloads to the edge device to gain independence and robustness. So let's look at a bit of the more benefits that you get from doing this instead of running everything in the cloud. And if we again take a look at our FixedIT data agent, then we can consider a case where we have an issue with our internet connection. If you were somehow running a cloud service pulling data through network APIs to get this kind of information about your devices, firstly, you probably wouldn't be able to get this kind of granular data using the network APIs, since the ACAP SDK allows you much closer integration with the device to get more information about it. But even if you did get this, it would mean that whenever you have an issue with your internet, you wouldn't have any data going into your platform, and you will get gaps in your graphs. And these kind of blind spots are particularly bad, since these kind of anomalies, like when you don't have any internet, those are typically the ones triggering other issues. So if you're debugging an issue, it's a good possibility that the root cause of it was that you lost internet. And then you have a gap on exactly the time that is interesting for you. So that would be very bad. And it's of course the same for all kinds of security analysis, where you would like to buffer video data instead to make sure that you don't have any gaps in your video for forensic investigations, for example. But with the power of an edge application that always runs in the camera, that means that this edge application will continue to collect metrics about the system, even if it is offline. And it can even do introspection of internet connectivity to debug why is the internet connectivity not working. And then it is saving this in a buffer. And as soon as we get internet connectivity again, it is pushing all this data retroactively and backfilling the gaps in the graphs, which means that you now have a complete log data for also the time with no internet connectivity. So let's again take a look here on the in the Grafana. So we have one of our devices here, the M1055. I know this one has been on an unstable network lately. So let's get over to our device detail, and we have already selected here the 9930, our M1055 camera. So we can see that we do actually have one gap here in the data. And if we look on the camera uptime, we can see that the reason there is a gap in the data is that at this point, the power was cut, and then the device wasn't running until at this point when it started again. So that of course means that if we don't have power to the device, if the device isn't running, then our application can't run either. So there's not a lot to do about that, apart from, of course, setting an extra battery-powered supply to camera device, for example. But if we look back here, we can see that here we had one power outage, which killed our device, but we got the power right back again after this, and it booted up again successful and started logging data. So we can see that we have both memory data and CPU data right after this power outage. But on the other hand, if we look at the network information on the DNS response time, so this is pinging a public DNS server to check the internet connectivity, and we can see the latency of the response time of the queries here. And here we can see the ratio of successful responses. Then we can see here that right about the time when we had a power outage, we also lost internet connectivity. And then we didn't have any internet for the following 20 hours or so. So despite having 20 hours with no internet connectivity whatsoever, we still managed to get all this data during this outage period because it was buffered up in the application and then backfilled to our dashboard as soon as the device got back online again. So this can be a really helpful debugging tool to help you investigate both post-mortem investigations if something has gone wrong, but also to proactively make sure that your devices are feeling well. And especially for ACAP developers, this is a very practical tool to make use of, both to see that you're not loading the device too high, which could cause robustness issues, but also to make sure that you don't load it too low and leave resources behind that you could have made use of. So for example, if you run your application, in this camera, you can see that we have 4 different CPU cores that we can make use of. And if you have a single thread application where one thread is a bottleneck, then you will see that only one of those has a low availability, while the other ones are still idling most of the time. And that means that there's a lot of extra compute power that you can make use of to optimize your application by making sure that you have an even distribution on all the different cores. So, cloud deployments. A lot of products today are building on cloud-based deployments, which essentially mean that you're treating your camera as a dumb device, just streaming RTSP, for example. And then you're streaming that over the internet, consuming high bandwidth to a cloud instance where you do the compute. And this often turns out to be quite expensive after a while. Hyperscalers like AWS are very good at making it very cheap in the beginning, and then the price steadily increases. The more you get tied up to it, the more expensive it gets. And then you might even push some data back to the site if that's where it is needed. So there's a lot of drawbacks of doing this approach, both from a scalability and from a robustness perspective. So the reason that most companies are implementing their product this way is that it's easy to do it that way. It's often the easiest way to build a product. And one of the reasons for that is that the hyperscalers have done an amazing job on building infrastructure, building reusable components, and making it very easy for you to develop products in the cloud. And you have a good support for all the open source frameworks and so forth. But what we are trying to do is to make it as easy as possible, as easy to do this on the edge device as it is to do it in the cloud now. And that was one of the reasons that we have implemented extended functionality in our applications that allow you to use them to help make things easier for you. So if we take a look at one use case, we have a GitHub account where we have a JSON file. We want to validate that the JSON file is always in a good state. And we do that using GitHub workflows, which allows us to run a job every time a file is changed on our main branch. And we always want this job to be green because typically people should open up pull request and verify that their code passes all the tests before they merge it to the main branch. So if someone doesn't do that, then we want to get notified as fast as possible. So why don't connect this to an axis strobe and set the color of it based on the status of this CI/CD job? So one way we could do this is to use a Python program, just as I did for the PTC control. We can use a Python program with VAPIX requests going to the device to set the color of it. And then that same Python program will make requests to the GitHub API to get the current status. But this means that we have this issue with, first we need to know where is my device located, which network is it available at, which customer did we send it to, which office is it sitting in, do we have different subnets? And secondly, we need to compensate for all these issues with firewall issues that we're not allowed to make requests from the cloud to the device and so forth. And we also need some kind of cloud server running all the time just to make these API requests. So in this case, it actually seems like the cloud doesn't offer the easy way to do it. It would be much easier if we just could write our application for the strobe itself, and then let the strobe make requests to the GitHub API to get the status and then updates its own color. That means that this strobe can be installed in any network. We can even pre-install the application, send the strobe to the customer, and all they need to do is to plug in the Ethernet cable and it will start working, showing the right color. And this doesn't, of course, go only for GitHub API. We could use any kind of API. It could be a weather API showing the status of the strobe based on if there's any warnings from our weather prediction services, for example. Or it could be any proprietary equipment that you might have with an API. So let's actually take a look at how we can implement this. But before we head into ACAP development, let's go back to our FixedIT data agent, since that one can actually be very helpful here. So in the FixedIT data agent, you have the ability to create your own scripted workflows for your own use cases that should be handled by the data agent directly on the device. So the way this works is that you can define different kind of inputs. So an input can, for example, be reading a file. It can be making an HTTP request to an API, or it can be to measure the latency of the internet, or essentially anything you can imagine. And then you define different kind of processing, different aggregators, different filters, and so forth to do transformations to this data that you get from the inputs. And then after that, you push the data to some kind of output. And there are loads of different outputs, for example, InfluxDB, which we use for the monitoring, MQTT, which is very common for IoT applications. It's a message publish subscribe protocol where you can send messages to a specific topic. Or you can do HTTP push and just send an HTTP message with the data. And a lot of other possibilities. But for this use case, it sounds very much like what we want to do. What we want to do is to have an HTTP input, which make a request to GitHub and gets the status of our job. We then want to do a transformation to transform the response we get from GitHub API to a color that our strobe should show. And then we want to use this color to send it to the VAPIX API, which will actually change the color of the strobe. So let's see if we can make this happen in a live demo. So I'm going here to the interface of our strobe. We see this is another IP address, the 4100 network strobe. And it's sitting here right behind me. You can see that it's currently not lit at all. And here we already have the Telegraph agent installed. And we can see that it's running 7 configured configuration files. If we take a look at files here, we can see that this is our standard monitoring workflow where it's collecting different kind of system metrics from the device and from the network. It's adding some tags. It has some agent configuration telling how often it should do the sampling and so forth. And then it is sending it to an output. In our case, we want to start from scratch, so let's just disable all of this. And now we should see that we get error messages here complaining about that there's no configuration paths or no configuration files to run because we have disabled everything. So let's then start with uploading files. So I have prepared a few different files here with different parts of the workflow. We could combine everything to one file if we want to do that. I chose to keep them separate to make it easier to enable and disable functionality bit by bit to test it. So let's start with the agent configuration. This tells the agent how often should it do the sampling. So in this case, we say every 5th second we should make a request to the API. And if we have a lot of devices, it might be good to add a jitter time, so not all devices are making it exactly every 5th second, because then you get very uneven load on your server. So here we say that we have a 1 second jitter, meaning that we will do the update between 4 to 6 seconds apart. So let's enable this. And if we go to the log now, we will see that we don't have any outputs. So every workflow we do need to have inputs and outputs. That's the minimum requirements. So let's upload and sorry, not this one, and GitHub inputs. So this file is making use of an HTTP input, and we have a URL to the GitHub API where I make use of environment variables that I set up before with my user and secret information and so forth. We give this data metric a name, and we tell it what fields we should collect. So if we enable this one, and we still need an output, we're going to start with a std out output just for debugging purposes. This will just write any data in our pipeline to the standard output, which will be visible in the user interface. So if I now go to the logs, we should see that it starts a new workflow, and at the top here we should hopefully soon see the standard output from the workflow. So there we can see that we get data from our API request. And this data includes a status, the job is completed, and it includes the conclusion, it was a successful job. And it also includes the name of the workflow and so forth. But in our case, we just have one. So this it's enough to just look at the conclusion to see if it was successful or not. So let's do the transformation to extract the color that we need. We're going to do this with a processing step. And as I said before, I'm a big fan of Python. So in this case, I'm going to use Starlark, which is kind of a domain-specific language, very similar to Python, but a bit more sandboxed. And it can be used to do custom transformation from messages. So we define a function here that will run for each metric that we get, meaning each API response that we get. And we will just extract the conclusion tag from it. And then we will compare this. We will create a color variable where we set the default value to yellow. And if it's successful, we will set it to green. If it's a failure, we will set it to red. And then we return this new metric. So if we go back to logs now, we should hopefully see that we get a much simpler message here instead. And there we see the simpler message. So we can see that this one just have one field, its name color, and its current value is green because the CI/CD job is currently in a good state. So now let's add the last interesting part here, which is the strobe output. So this is the one that will take this color value and affect the state of the strobe. And I said before that there is an HTTP output. In this case, we can't make use of that directly because the HTTP output makes some assumptions on how the data format should look like. And the VAPIX API, on the other hand, make other assumptions on how the data that you send to it should look like, and there's no overlap between those two. But with this application, that's not an issue because we always have the exec plugin that we can fall back to, which means that we can just execute a script to do whatever we want to. So in this case, we say that we should execute a script called trigger_strobe.shell. We should only send it the data from the workflow color metrics, which is our transformed color. We should send data in JSON format. We disable batch format because normally the Telegraph agent would batch data and send a lot of them in the same request to make sure that you don't get too many requests over the network. But in this case, since it's real-time data, we don't really care about historical values. We just want the latest value to be pushed as fast as possible. So that's why we disable batch processing, and we're saying that we should just have one metric in the buffer. So of course, we also need this script. So I'm going to upload a helper file. I'm going to select the trigger strobe script, and I'm going to mark it executable since it should be an executable script. So now we have the script here, and we can take a look at it, and we see that it's a shell script. So this is one important thing to remember, that when you start doing shell scripting in the Access cameras, one thing that you need to know is that they don't have bash. So if you're a Linux person, you're probably very used to using bash for scripting, but there's no bash interpreter in the Access cameras. There is, however, a shell interpreter. So it's a different flavor of quite similar language. And the other thing is that you need to be aware of what shell commands are available in the target device. And this is unfortunately differing a little bit between different versions of Access OS, for example. And there's no complete list from Access on what available commands is supported in different OS versions. So that means that if you're using shell scripts, then you need to be a bit more careful with testing and so forth to make sure that it will be a portable solution that you're creating. In this case, we have a bit of input validation. We check that we have environment variables set up. I have set up those before too. And then we are reading the JSON input, just checking that we got some input, and then we are using JQ, JSON query, to get the color of the just the color string from the message. And here you should be aware of that older Access OS versions didn't come with the JQ command. So that is one of those things that make it less portable if you use this specific command. You could, for example, use Z instead or something like that to extract the interesting value to make it more portable. And then we are defining a function here that will make our network API request. So this is very similar to the Python script we did for PTC. It's just that now we're using curl instead, which is the command line utility for doing web requests. And we're sending it to the Siren and Light API. And we give it a profile and an action on or off or start or stop as input to this function. And then we call this function for the particular color that we want to enable with the start command. And also the way the access strobe is designed, you need to disable the other colors. So if we want to show green, then we disable the yellow and red. If we want to show yellow, then we disable the green and red and so forth. So let's enable this one. And now you should hopefully see the strobe here behind me light up very soon. We can go to the logs in the meantime to see the workflow being created. And yep, there you see a green light from our strobe. So let's now go to our Git repository and see if we can actually make the strobe change color. So this is the JSON file that our CI/CD job is testing for validity. So I'm going to remove one of the quotes here, which renders this invalid JSON. And if we go to the action tabs, we should see that we get a new job getting started, and the strobe here should hopefully change to a yellow state. And there is yellow. And yeah, there it turns red, indicating that the job isn't passing. So if I reload my page here, we see that it's now a red light in GitHub too. So I'm not sure how well you see my video feed here, so I'm just going to stop the screen sharing, which means that you see the video in full view. And now I'm going to repeat this process and make the JSON data valid again. So I'm currently editing the JSON file and committing the changes. So now you should see it's going back to yellow since a new job is running. Here we have yellow light, and hopefully it should turn to green since the JSON is now valid. And there it's green. Excellent. So let's go back to screen sharing. And the last step we would do here is just to disable this continuous logging. So we can do that by disabling the standard output. And now the workflow will continue to work. So let's go back to the presentation. This was very quick and easy to do this. It's essentially only the imagination that can put limitations on what you can do with these solutions. And the benefits of doing this with a data agent compared to just writing a massive bash script and run that as an ACAP application, which is what we will look at next, is of course the robustness, error handling, durability, and so forth. There's a lot of functionality built into the data agent on how to handle retries, for example, if the input API doesn't respond. It's easy to add buffers for storing metrics locally and send them later if you get internet back. It's yeah, there's a lot of functionality that gives it a robustness and makes it suitable for production use. And it's also very configurable in terms of that you can easily make changes and add new functionality, make use of all the different input and output plugins that are available and so forth. So it's a very flexible and powerful solution. But it is, of course, not a solution for all the problems in the world. There are still things that we need to do by creating our own applications. And computer vision is typically one of those, where we need to read an input image and decode or analyze the content of the image, and then apply some business logic and do something based on the result. So for example, we talked about QR code reading before. So let's head back to our OPIC 9 camera here, the Q1728. And here, if we go to the live view, we can see that we have 2 QR codes currently on the door. And if I go to app and I enable our QR code reader application, then we should see that it starts writing an overlay on the video feed, and it detects the QR codes. It draws an overlay to mark the position of them, and it shows the decoded value, which in this case is the URL to our website. So if you want to do something like this, then you of course need to create your own ACAP application. But with that said, you can of course combine this with a data agent and utilize the strength of the data agent as a data adapter. So you could do the analyzing in your application and then write the detections to the data agent and use that one as an adapter to bridge to different protocols and different systems that your customers might have. So that way it's easy to both integrate with different kind of systems, but also do different kind of simple transformations, filtering, and so forth in the workflow without actually making changes to the application. So let's dive into how do we create our own ACAP application. The process is actually quite simple, and it's not a lot of tools you need, so it's super easy to get started actually. Essentially what you need to do is to find the right documentation. You need to install the tools that you need, and then you need to create the files for the application, and you build the application, and you're up and running. So sounds like something you can do in 5 minutes, and with a few minutes over the time already, let's make this a very quick demo. So I have a VS Code, or rather cursor window here with an empty folder currently containing nothing at all. And since I don't remember by heart how to create ACAP applications, despite having done it hundreds of times, I luckily have, let's see, we should have our learning portal. So here we have our learning portal. And here we can find our ACAP intro course, which is an amazing utility to get you started with ACAP development. It's a video and text-based course where we go through everything from introducing ACAP applications and the Access OS, different SDKs and so forth, and explaining where to find the documentation with links to all the relevant documentation and so forth. We explain how to use the cameras, both how to physically install them, showing with videos how to install it with PoE injectors, how to install it directly to your camera, how to connect it directly to a computer, how to set up the CP servers for easier debugging and so forth. And also how to use the Access Virtual Loan tool if you don't have any camera at all, so that you can get started by yourself. What we're interested in is this section here, build and run your first ACAP application. So if we scroll past the videos here, we will see this is the minimal structure that we need for an ACAP application. And the first file we need is a Docker file. And this is because the SDK is Docker-based. So the way we use the SDK is essentially to inherit or extend the Docker image for that SDK. So let's start by creating this Docker file and saying that we should use the latest version of the ACAP native SDK for the ONVIF 7HF architecture. And this is also one of the things that we handle in this intro course, explaining how you can use or what the different architectures are and how you find the relevant information and so forth. Second thing we need is a manifest file. This tells both the ACAP build command metadata about your application, but also when you install the application, this is used. And this is the minimal version of it. So let's create the app folder and create the manifest.json file. So here we specify a schema of the manifest file. There's also something explained in the e-learning portal how you can find the different schemas and find what values and tags are valid in that schema. We set a name of our application. This is important since it needs to match the binary that we're creating. And then we have some compatibility version. We say that it shouldn't be restarted. It should just run once. And we set a vendor and version of the application. We also need a license file for open source licenses. It doesn't need to contain anything interesting, but it has to be a file and it can't be empty, otherwise we get complaints. And the content of this will be available if you go to the open source license page in the camera after installing the application. I'm just going to add a to-do. And then we need a make file. And a make file is what will actually be executed by the ACAP build command that we can see in the Docker file here. Here we are sourcing the ACAP SDK to get the tools, and then we run the ACAP build command. And this one will first run the make file, the default make target, and then it will package all the files in an EAP package that can be installed in the camera. So let's make sure to get correct on space and tabs here, and we don't need that one. So what we're doing here is that we are creating a simple shell file, which is just echoing hello world, and we're naming it here the same thing as we used in the manifest, and then we're marking it executable. If you had a C application, this is where you would actually do a cross compilation of your application. So for now, I'm just going to build this using the FixedIT CLI tool, but you could just as well build this with a normal workflow of using Docker build and so forth. It's just a few more steps involved. And now we see that we got this AAP file created. I'm just going to copy this AAP file to my downloads folder to make it easy to access from the browser. And we're going to I already had it installed here, so let's uninstall it just to make sure that we get a fresh install from the one that we just built. And then we're going to install our application that we just created. And we can see that we have my first app, version, and vendor that I specified. And here we have the license file, and we have the app log. And we're going to start this and have a look in the application log. And hopefully we should see a hello world message being printed here when the application starts. And here we go, we have an hello world message from the application. So that's how easy it is to create your first ACAP application. And then the more complex thing is, of course, to make it robust, make it portable, make it durable, and so forth. And you can see here, kind of, we have some missing parts in this, I see now in this slide, but our process for ensuring quality in the application is quite extensive. So it's a quite big gap between just creating your first POC application and creating something that you can actually sell as a product. And that is part of why we created a fixed data agent, for example, but also why we provide a lot of different tools that are available to you if you develop your own applications. So I'm running low on time, so I'm going to step through this quickly, but essentially, how can FixedIT help you if you want to develop applications? We are a bunch of experts on the ACAP application platform. Personally, I have done ACAP development for 10 years, started at a company called Coordinatics, doing people counters for the Axis cameras. Then I worked for Axis, doing their own analytics applications. And now I'm working at FixedIT with ACAP applications. And we do everything from developer education, training, reusable building blocks that you can use to build your own solutions. And we can even do custom ACAP development specifically for you. The easiest way to get started is our e-learning platform. Our intro course is $12 per month, so that's an obvious buy if you're going to even explore the ACAP application platform. If you are more dedicated, that now you're actually getting started with your team, then we have what we call ACAP Developer Acceleration Program, which includes technical assistance by our ACAP developers, a lot of instructions and educational material, and different small tools and scripts that are very useful when developing ACAP applications, and also a bunch of other things that are very useful. So that can greatly increase your pace and success rate of your ACAP development projects. And finally, if you want to have a custom application developed, if no one else on the market is providing that application, then we can build specifically for you and help you find out the right requirements and the best solution that will actually solve your problem in the most affordable and effective way possible. So that was everything from me at FixedIT.ai about creating your own ACAP applications. So let's see if we have any questions. Doesn't seem like we have any questions today, so that was everything from this webinar then. Thank you very much for watching the webinar, and I wish you good luck in your future development journey, regardless if you choose the path of VAPIX, ONVIF, data agent, or writing your own application from scratch. So good luck and have fun in your projects.